All right, ladies and gentlemen, we will be looking at the last part of double replacement reactions, and that is acid-base reactions. Now, acid-base reactions are going to, in the lab, look very similar to a double replacement reaction, but they would look as if nothing happened. And this is where kind of knowing what you're dealing with helps out a lot. And so having seen maybe some in your past experiences, you should be able to recognize some of these. However, they don't look like much happens, even though there is a lot that actually does happen. So let's get started in defining what an acid and a base actually is. So there are two different routes that you can take with the definition of an acid or a base. Swedish physicist Arrhenius defined acids as a substance that increases the concentration of the H plus ion when dissolved in water, where a Danish chemist Bronsted and a British chemist Lowry defined it as proton donors. Now, if we remember back to naming and earlier on, we would have remembered that, and actually the H plus ion actually is just a proton, and so we do have to be, they work are very similar. So the definitions aren't really different. They're similar in that they're talking about the same thing. It's just what they're defining or what they're using as that definition for the what to look at it as. And so there's two different routes. One's dealing with usually just the hydrogen that's involved. The other one's looking at protons because other things could be deemed as a proton donor and therefore making it act as if it were an acid. And as we can see with the definition of a base, Arrhenius says that it's a hydroxide increases the hydroxide concentration when dissolved in water, whereas Bronsted-Lowry defines it as the proton acceptor. Something that we've looked at before is the litmus paper. The litmus paper will turn blue in a base, or if it's already blue, it'll just look wet. In an acid, blue litmus paper turns pink, and in an acid, red litmus paper will turn, well, looking just wet. And so sometimes if you are suspecting of one or the other, that's what we did. In the copper recovery lab, we did a lab that had us looking at the we wanted to make sure that it was a base, so we had to use red litmus paper and see it turn blue. Both of them, that's a proton acceptor with that, and or a hydroxide increaser, I guess, is how, depending on how you want to look at it. We're not going to get too much involved in the differences between acids and bases. That would be something that we would do later on, but we just don't get there or have not gotten there in years past. And so we're not going to worry about it. We just need to know that there are things that are considered to be acids and there are things that are considered to be bases. How they're defined is an important part. Some of the strong acids that we deal with on an everyday basis: hydrochloric acid, usually in the lab; hydrobromic or hydroiodic, not so much, aren't very common in the lab. We've used nitric acid in the lab, and that was that helped to dissolve the copper in that lab. Sulfuric acid, also sometimes known as battery acid, not one that we utilize a lot in the lab just because of how dangerous it actually can be. We also would have chloric acid and perchloric acid, not commonly used in our lab, but you would see them in a lot of different other manners. Strong bases are usually your alkali metals, and your alkali metals are going to be your group 1s. If you remember back from in an earlier unit, or talking about your periodic table, other strong hydroxide bases are usually calcium and strontium and barium hydroxides as well. Now, ammonia would also almost be in there as well. Ammonia hydroxide is a pretty strong base, and actually it can be sometimes used in some different wood products and some of those types of things, and it's really cool to kind of see as if you were ever kind of pulls some different oils out and stains them and kind of as a different burn, how it looks. But it is very interesting and cool. What's actually happening in an acid-base reaction is that, and here we're using again ammonium as the ammonia to make ammonium and hydroxide. We can see that the hydrogen is going to the ammonium, and therefore is the hydrogen donor, or you're going to have that proton donor and the proton acceptor. So we can see that water in this case is acting as the acid, and so that's one thing that a lot of people ask, well, what is water? Is it an acid or is it a base? Well, it really depends on what it's in contact with. If water is in the presence of a base, such as ammonium, or ammonia, it will act as the acid, and if it's in the presence of an acid, it actually acts as a base. That's why water is kind of unique in that it does serve both purposes. Kind of has that pH of 7. And this happens, kind of, we can see this back arrow is that it forms a certain level of equalness, and that we have kind of both are happening at the same time, and we do that. Now, this is how the ammonium ion is formed, and we end up getting the hydroxide. We can actually reduce this down to get the ammonium hydroxide to come together as well, even. And it does, again, it forms a pretty nasty base with that. Both of them are considered to be not fully super strong, although I would consider them strong for that. And here we can see now according to both versions, or both parts of both definitions of an acid and a base, that both of them are taken into account here, where we have water being the proton donor, and ammonia being the proton acceptor. We're increasing the amount of hydroxide on the other side, and so we have both of this happening, which again is just a little bit of kind of knowing what to look for. Now, the generalization general reaction does actually look very similar to that of a double replacement reaction, in that the hydrogen is working with the A, whatever A is, and then B is then dancing with the hydroxide. Now, they swing their partners do-si-do, and then B is then dances with the A, whatever it may be, and then water is given off. Now, what confuses sometimes students is that sometimes what will happen is that students will write it out as HOH and then forget that that is H2O. So there does become a little bit of a kind of disconnect between kind of knowing that HOH is actually H2O, and you can kind of combine those H's to make that there. And this is considered to be a neutralization reaction. You would not, and as we look, we don't form a precipitate, but if we looked at the net ionic equation, water, because it's a liquid, would not be in its form, and instead all you would say is that you have a acid coming together with a base to form water. Everything else would be kind of spectator ions here. It is a nice little way to suggest that if you are going to balance a neutralization reaction, balance out the salt first, and this would be considered your salt because it's ionic with that as well. And so we do need to be mindful of that and balance out your salt. And we'll do some examples of that in just a little bit. So, and then the water will, so for the most part, kind of find its way out or balance itself out. So we'll look at that a little bit further. So let's try some out. We'll start off with a very simple one in that we will have hydrochloric acid and sodium hydroxide coming together and forming. And we know when in a neutralization reaction we have an acid. We know we have an acid because we have the H written first, okay? Being able to identify your H's, your acids, and therefore a base. And usually if you have an acid, there's going to be a base present. It's just how severe or how strong of a base is there. The other one is probably going to act as a base if not. And so when we see that we have this, that hydrogen and hydroxide are going to form our H2O. That's going to be our liquid. Again, I utilize a kind of more of a cursive L for my writing so that we don't confuse it with anything else. And then sodium chloride is my salt, and that would be aqueous. And this first problem here is balanced as it is written in, so we don't actually have to worry about doing any extra balancing with that. Here we have sulfuric, the next one we have sulfuric acid reacting with a calcium hydroxide. Water, again, because of the fact that we're using hydroxides and we're using water, or I'm sorry, an acid, we're going to form our water with that. I should probably write that a little bit farther because I'm pretty sure we're going to have to do some balancing out here. And so my H2O, liquid, and then because calcium has a charge of 2, because that's where this 2 came from. That 2 came from the calcium in a reverse crisscross, and that 2 came from the sulfate in the reverse crisscross, and we'll be able to see that. And so we'll see the calcium and the sulfate form that. And that would also be an aqueous solution. I'll just write a little AQ underneath here. And so now we need to balance it out. Now, balancing it out shouldn't be too bad. We have two hydrogen here, 2 hydrogen there, and it makes 4, and 2 oxygen, which will mean that a 2 should balance out. And so it works out fairly nicely. The next one might not, and then sometimes that's just how, as we've seen, balancing chemical reactions just work out that way with that. In the next example, again, we have an acid based on the H being written out there and the hydroxide ion there. I'm going to write out my potassium phosphate first, and from there we see I got a potassium phosphate, and that is going to be aqueous, and then that's going to have H2O and give me that as a liquid. Now I have to balance this out. The suggestion was to balance out your salt first. So to do that, I will need to put a 3 in front of my potassium hydroxide to make sure that I have the proper number of potassium. This now leads me to see that the only thing I need to put in front of my water, because I have 6 hydrogen on one side and 3 oxygen on the reactant side, is a 3 in front of my H2O on the product side to balance it out. Now, some chemical reactions, as you would guess, don't always give you exactly what you suspect. And one of those is the reaction of a calcium carbonate reacting with hydrochloric acid. We do get the calcium chloride, but we don't get the carbonic acid as we would suspect, and that's the H2CO3. That would be their carbonic acid there. And so that's not present. A lot of you should have seen this, and a lot of students in their mineral identification and early on in either 8th grade or ninth grade will do a mineral identification, and with that they'll take a diluted acid, hydrochloric acid, and react it with limestone, calcium carbonate, and what happens is that it effervescence or fizzes, and that fizzing is actually when it gives off the carbon dioxide. And what else is a neutralization reaction going to give you? But water as well. And so we do have those there. That's why we go into the lab. That's why we see these things happening. We'll see this again. I'll try to point it out in a lab that we do later on as well. That why does we see this effervescence and this bubbling and fizzing, and it's again because carbon dioxide is being given off and water. And so both of these would be present in there, and so you would know actually that you have a carbonate present, an acid and a carbonate there, because in the net ionic equation, you would actually not, and I don't think, the only thing that would cancel out would be the chlorine there. So it would be a little bit more intense. This isn't the only one that doesn't always give us the unexpected or kind of something that where we have to see it to know it, and that's why we do these. Here are a couple other ones as well. We don't do these in the lab just for the simple fact that they can become very not very pleasant. They give off a very gross gas, especially the latter one here. We won't see these very often. They're just there for our understanding, and so that we do see that it doesn't always happen. And a lot of times it will happen with some of those bigger polyatomic ions that aren't in these strong acids and or a strong base, even though we have the iodic acid is our strong acid in this one. It's the strontium sulfite that definitely messes with this a little bit. And that's why, again, this is why we have to go into the lab. It really helps us see some of these. We're not going to do these in the lab because, as it says, becoming very unpopular is quite the understatement. You would be very unpopular because of just the pure sulfur smell. I think about if you've ever been to the sulfur pits. What you're smelling is a lot of this gas, and it's just really gross. Some people can handle it in small quantities. Some people cannot. And that is why it should definitely be carried out in the hood. It can, to the point, even take your breath away. And that you can, as you can see, since oxygen's not being present, and it would react with some of it as well. It would take your breath away and could lead to some damages with that. So when we now that we're done with our acids and bases, I believe we should be able to start the next lab, and that would be our chemical reactions lab. It's a fairly large lab that has a lot of different double replacement reactions, both acids with acids base, neutralization, and then also precipitation reactions, and some of those that you should be able to try and either predict and then go into the lab and see, does this even actually happen? Because that's always the other thing about chemistry. Even though we think something should happen, it doesn't always work out the way we want it to, and that becomes then the why didn't it work out? Or we saw something that we shouldn't have, the why do we see certain things happening and other things not happening? And I think that just really becomes the best part of chemistry is okay, that didn't happen, why? And hopefully you'll see some of those in your precipitation reactions.